Before we get started with the subject on wave mechanics, I just would like to take some time to introduce you to the basics of fluid mechanics. You have a number of textbooks, internet facilities where you have a number of lectures, PDF files, chapter wise, and I am sure that all these things, all this material would be quite helpful in understanding the subject fluid mechanics. Before we get into the wave mechanics, what I have tried to do is just to bring out some of the essential, most essential aspects of this subject, which actually is needed for the bigger topic, that is the wave mechanics. So I start with the general aspect. The behavior of ocean waves, or the behavior of waves in the ocean, governs the driving forces responsible for the different kinds of phenomena in the marine environment. The different kinds of phenomena, that is starting with how the waves are generated, how they propagate, how they form and then how they propagate, and when they propagate what are all the kinds of deformations or phenomena it would undergo in the absence or in the presence of any obstructions. All these things we will be discussing later. So in general, in order to understand all those phenomena, the driving forces are very important, and the driving forces are governed by the basic fluid mechanics. So a variety of structures are deployed or installed in the ocean, the design of which needs an in-depth knowledge on the characteristics of waves, which in turn require understanding of the basics of fluid mechanics. So this is accomplished by providing an overview of on the fluid mechanics aspect, so that it allows the reader to understand the principles underlying in the mechanics of ocean waves and its motion in deep as well as in coastal waters. So the purpose for going through a recourse to the fluid mechanics has been highlighted. So we get started. We have three states of matter that exist in nature, namely solid, gas and liquid. So liquid and gas are termed as fluids which undergo deformation under the action of shear stresses or shear forces. Most of them are self-explanatory, although they are self-explanatory. I just briefly discuss about some of these aspects. Now the main distinction between a liquid and a gas lies in the rate of change of density, that is, the density of the gas changes more rapidly or more readily than that of a liquid. So that is the rate at change, a rate at which the change in the density takes place, that really governs whether the fluid is a liquid or it is a gas. If the change of density of a fluid is negligible, then we say that it is incompressible, it is defined as incompressible. So let us go to the next slide. We basically have two broadly classified fluids, types of fluids. A fluid that has no viscosity, no surface tension and is incompressible is termed as ideal fluid. For such a fluid, no resistance is encountered as it moves. Ideal fluid does not change in nature. However, fluids with low viscosity, such as that of such as air, water may however be treated as an ideal fluid, which is reasonable and well accepted assumption. A fluid that has viscosity, surface tension and is incompressible, which do exist in nature, is termed as practical fluids or real fluids. These are the basic definitions of a real fluid and an ideal fluid. Please note, very often some of the students they make a mistake of calling a ideal fluid as ideal flow. Flow is not ideal, it is only the fluid which is ideal. Flow can be irrotational, rotational. So next, history of fluid mechanics in brief. There are a few books which has beautifully described about the history of fluid mechanics quite in detail, and which is quite interesting also. But what I have done is I have just discussed in brief the theories of a real or real fluid of Euler and Bernoulli. These are the scientists established, they established in the mid 18th century, and these theories included the conservation of laws of for mass and momentum or kinetic energy. Then this achievement was followed by considerable progress towards the formulation of several empirical formulae in the field of fluid mechanics as well as in hydraulics. Many of you might have heard Navier and Stokes. It was Navier, a French civil engineer, during the early 19th century found that the real fluid theory does not yield a good estimation of forces on structures due to fluid flow when the design of for a bridge across river Seine was made. So this was realized by Navier later, and this allowed the viscous flow theory, in which a viscous term to the momentum conservation equation was developed by Navier in 1822. I am not showing any equation, I am just giving you some of the background. Then just few years around the same time, or maybe 20 years later, it was Stokes from England who also developed viscous flow theory. The momentum conservation equation for describing the viscous flow, which is still in use, is therefore named after them and is termed as Navier-Stokes equation. Very often you see what is Navier-Stokes. Many of the equations, many of the phenomena can be well described by Navier-Stokes equation. Having gone through the basics of fluid mechanics, very brief, we will just look into the types of flow. We have broadly classified 8 types of flows: steady and unsteady, uniform or non-uniform, rotational or irrotational, laminar or turbulent. Remember, these are flows. What we had seen earlier is the fluid, ideal and real fluid. Now flows are given here 8 forms, but there are some combinations that are also possible. So we will just examine one by one the types of flow. So steady and unsteady flow. Fluid characteristics such as velocity, pressure, density, temperature etc. at any point do not change in time. For example, water moving with a constant discharge rate. So at any point when you consider the flow of water with constant discharge rate, or in general, that is only an example, in general for this kind of a flow at any point x, y, z, the rate of change with respect to time, the rate of change of the property which we are discussing, be it u, p or rho, with respect to time is 0, that is do not change with time. If it is changing with time, if it changes with time, what is it? Unsteady flow. So for example, if it changes with time, then for example here I have taken the behavior of ocean waves. What do you mean by behavior, why ocean waves are unsteady? You will see that later how a wave varies. In the case of a regular wave, if you measure the waves in the deep ocean, so this is the surface elevation, and you see that the surface elevation is going to vary with respect to time. When you measure in the open ocean, or if you later you will also see that the waves are can be this kind of a wave can approximately said to be represented, can be represented as a sinusoidal wave. So these waves, you see that when they are moving on the surface, it will have its particle velocities and other characteristics that will be changing within the fluid medium. So all those changes, like the change in the pressure etc. or velocities, will all be changing with respect to time. So that is why we say that it is an unsteady flow. Now uniform flow at any given instant of time, when the fluid particles as stated earlier, u, pressure, density etc., does not change in both magnitude and direction from time to time, so from point to point, within a fluid, the flow is said to be, that is why we are showing it as dou u by dou s, s is with respect to space. So the variation of velocity with respect to space at any given point of time is going to be equal to 0. Okay. So non-uniform flow, if the velocity changes, if the velocity of fluid, when I say velocity it also includes the other properties of the fluid, if the velocity of fluid changes from point to point at any given time instant, then it is called as non-uniform flow. The ones which are having the red color font, that shows only the examples for the different kinds of flows. Here in the case of non-uniform flow, flow of liquid under pressure through long pipelines of varying diameter. Suppose if the diameter is constant, if this diameter is constant, the same flow of fluid under pressure will be uniform flow. So now this is constant dia, and now we have varying dia, that is going to take care of whether the flow is going to be non-uniform or uniform. Okay. Now under steady or unsteady and uniform or non-uniform flow can exist independently of each other, that is you can either have steady or unsteady, uniform or non-uniform, but they can also have combinations, combinations are also possible. So for example, if you have a flow of liquid under a constant rate and it is in a long pipeline, constant diameter. So you see that constant rate, constant diameter. So here I have said varying diameter, constant diameter. So if it is a constant rate in a long diameter, but the flow is steady, I mean the diameter is constant, then you have steady uniform flow. Is that clear? Then the flow of liquid, whatever I have highlighted, that is very important. So the flow of a liquid at a constant rate through a conical pipe, that is steady because constant rate is there. So you have a constant rate here, but the shape of the pipe is different. So the shape of the pipe dictates whether the flow is going to be uniform or non-uniform, and the rate at which it is pumped, that is going to be controlling whether the flow is going to be steady or unsteady. So you have a control of the types of flow you want to generate. So with the changing rate of flow, these cases become unsteady, uniform and unsteady, become unsteady, uniform or unsteady or non-uniform flow. All these cases are possible. Is that clear? So although these are very fundamental, I have noticed that there is a kind of confusion some of the students express when they are asked for some questions, they fumble and they get very easily confused between uniform, steady, unsteady, non-uniform. So please remember the kinds of examples, the example which is if you remember the example, that will clearly indicate the type of flows, etc. You have what is meant by rotational flow. A flow is said to be rotational if the fluid particles while moving in the direction of flow rotate about their mass centers, that is natural. So it has to rotate about its mass center. So for example, a liquid in a rotating tank, so that is a classical example for an irrotational for a rotational flow. Very often we deal with irrotational flow, and some of the derivations you will start, the flow is ideal, fluid is ideal, flow is irrotational. For example, when we derive the velocity potential, in order to understand the wave mechanics, how the wave propagates, etc., we will be forced to derive a velocity potential. The basic assumption there is the fluid is ideal, flow is irrotational. So the fluid particles while moving in the direction of flow do not rotate about their mass centers. This type of flow exists only in case of ideal fluid. Why ideal fluid? Only in ideal fluid there is no tangential or shear stresses that would occur. Although the subject is quite simple, you should remember all these definitions forever. So it says that the flow, this type of flow, that is irrotational flow, exists only in the case of ideal fluid for which no tangential or shear stresses occur. But if the viscosity of the fluid is very small or very less or does not have much of significance, then in that case even this kind of flow can be assumed even in the case of real fluids. For example, when I told in the beginning, air and water are assumed as ideal fluids because it has very low viscosity, etc. So it is only an assumption, and the assumption is quite acceptable. Now for a fluid flow to be irrotational, the following conditions are to be satisfied. What are the following conditions? That is, it may easily be proved that the rotational components about axis parallel to y and x or x and y axis can be as said here, dou y, that is wx half into similarly for wy along the y axis and this with respect to the x axis. So if at every point in a fluid which is flowing, the rotational components as indicated here, wx equal to 0, wy is equal to 0 and wz equal to 0, and then automatically you will get this expressions on the right hand side, that is dou w by dou y equal to dou v by dou z. So if when you have the particle motion or the velocities of the particle in a fluid moving in the x direction and y direction. So you have u and v, u, v and w. Then with this, using this differentiation etc., this relationship, you will be in a position to find out whether the flow with that kind of velocities will that be following, can it be termed as an irrotational flow or otherwise, by simply trying to get that this relationship through. Is that all right? So u, v, w are the velocities in the x, y, z directions. Now we move on to laminar flow. A flow is said to be laminar if the fluid particles move along straight parallel paths in layers. That is, when you visually see, the particles will be moving in layers. This can easily be simulated in a lab by having a controlled discharge over a glass tube, and this is a classical example, that is a classical exercise done in undergraduate course. So you can see that if the fluid particles are move along straight parallel paths in layers such that the paths of the individual fluid particles do not cross the neighboring particles. So each particle will be moving in layers or in laminae. In other words, the fluids appear to be moving to move by sliding laminations, okay, so something like sliding over, okay. So this type of flow occurs when viscous force dominate the inertia force, and particularly at low velocities. So what do? You have a tube and you inject some dye so that you can see the path and you control your Reynolds apparatus. This is what I am trying to explain. So you can just try to control your discharge, and if the discharge is very less and you control it in such a way that you can easily visualize the flow that is moving, okay, in kind of you can generate a kind of a laminar flow. So laminar flow can occur in flow through pipes or open channels or even through porous medium. Of course, laminar flows are much easier for us to solve compared to turbulent flows. Turbulent flows, this is just an opposite to your laminar flow. Fluid motion is said to be turbulent when the fluid particles move an entirely random or disorderly manner that results in a rapid and continuous mixing of fluid leading to momentum transfer as flow occurs. See, as far as this turbulent flow is concerned, it has a kind of a direct connection with our kind of studies, particularly when it is either wave mechanics or coastal engineering. So, for some of this turbulent flow you will be coming across while we are discussing, while I am describing about some of the phenomena that we come across in both the subjects like wave mechanics as well as in the field of coastal engineering. A distinguished characteristic of turbulence is its irregularity. There being no definite frequency as in the case of wave motion and no observable pattern as in the case of large eddies. Is that clear? So eddies or vortices of different shapes and sizes are present over large distances in such a fluid flow. Flow in natural streams, artificial channels, sewers, etc. are all few examples of turbulent flow. It is quite difficult to deal with turbulent flow compared to laminar flow, because it is laminar flow is a kind of a flow which can be tamed, whereas turbulent flow is very difficult to tame the type of flow because it is going to be moving in random. So having seen the types of flows in brief, we will just look at one of the important equation, that is the continuity equation, and continuity equation, that is it speaks or it tells about the conservation of mass. Now let me so I am considering a point A, B, C and D. Now this is A dash, B dash, C dash and D dash, and I am identifying an element, a point at this location at the center, and my axis is x and y, and of course you have the z. Let me take this distance as delta x and this will be delta y and I have delta z. So my point here is defined as P xyz. Now when you consider an elementary rectangular parallelepiped with sides as indicated, the planes are also indicated here, which we are going to consider. The flow is from left to right and it starts at the center point. Consider a plane running at the center point. So through this plane at this point, center point, the flow is taking place and the mass of the fluid will be as indicated here. So now this is what we consider that u, v and w are the velocities in the x, y, z direction and rho is the mass density. So the mass of the fluid that is going to pass per unit time through the phase normal to the x axis at point P will be rho into u into delta y and delta z, that is the area, this is the area. Now what is the mass, what is then the mass of the fluid that is flowing per unit time into this through the phase ABC D. So we are talking about this phase. This phase will be the mass, that is rho u delta y and delta z, that will be entering. But what about the rate of change? Rate of change will be with respect to the x direction, that has to be added. So we add that as delta x dou by dou x with respect to x, okay, this is the mass, but over what distance? Over, because the point is in the center, the distance will be delta x by 2, but it will have a negative sign because the reference point which we have taken is the center and the phase which we have considered is the on the left hand side, that is on the other side of the opposite side of with that of the direction of flow, and that is the reason why we have minus delta x by 2. Is there any doubts in this? So I write this as into plus dou by dou x so this will be the mass fluid flowing per unit time through the phase A, B, C, D, okay. Now you repeat the same thing by considering this area, this phase. This phase will be practically the same except that because it is on the side towards a positive direction of the flow, so you will have the same thing that is what is written here. So you have fluid flow per unit time in this over this phase and over this phase. Is that clear? We have established that. Now having established that, we need to get the net mass of fluid that has remained in the fluid medium. After all, we are considering this as a fluid medium. And what is the net mass of fluid that has remained in this fluid medium per unit time through this pair of phases, because we are taking only these two pair of phases. So that will be this minus this, then you will get as shown here. But then delta x is not going to be a function of x, because we have considered an element of fluid. When we consider an element of fluid, the lengths are fixed, hence the delta x can be removed out, but we retain the variation of u and density with respect to time, sorry, with respect to space here, okay, with respect to space it is retained. Yeah, this is what I have just now explained. Now by applying the same procedure, the net mass that remains through other two phases can also be obtained. Instead of here we have u, so you will have v and w, that is all. So we consider this phase and this phase. So this phase and this phase, and similarly the other two phases, that is this phase and the other phase behind the board. So by adding all these three, we get the net total mass of fluid that has remained in the cube per unit time, which is going to be as indicated here, not indicated, as calculated or as derived. Are there any doubts? So what does the conservation say, conservation law? Since the fluid is neither created nor destroyed in the cube, any increase in the mass of fluid contained in this space per unit time is equal to the net total mass of fluid that has remained in the cube per unit. So there is no creation or removal, okay, no addition or reduction or removal. So now the mass of the fluid in the cube and its rate increase with respect to time, the total mass, that is you have rho into d rho t, that is with respect to time, and this is going to be your mass. So the mass of the fluid in the cube and its rate of increase with time can be easily expressed as shown here. Now we need to equate, in order to have the conservation law satisfied, we have to equate this with the earlier expression, which is now going to be written as this, that is a summation of the net mass that has remained in the remained in the cube, considering all the 6 phases, I mean 3 pair of phases. So now this is the final expression which we have arrived. Now divide both sides of the above expression by the volume. Once you do that, you are going to get, taking the limit that the fluid medium shrinks to the point P, the entire fluid medium, that we have now expanded the whole thing just to understand how these different components act. Now if you assume, taking the limit so that the entire fluid medium shrinks to point P, the continuity equation is obtained as we have seen earlier, and this is going to be the continuity equation. This equation now represents the continuity equation. In its most general form is applicable for steady as well as unsteady flow, uniform flow, non-uniform flow, compressible as well as incompressible. See, you the variation with respect to time is considered there, variation with respect to space is considered there. So, all these factors are included. So, you can apply it for compressible as well as for incompressible fluids, and it is applicable for all types of flows which we had discussed so far. So, in the case of steady flow, we know that dou rho or dou rho by dou t has to be equal to 0. So, the above equation then becomes as shown here. So, this will be applicable for both compressible and incompressible flow, incompressible fluid, but only steady flow is applicable. It can be applicable only for. So, now you remove for example, for an incompressible fluid, the mass density will not be changing with respect to x, y, z and t, and hence the above equation can be simplified as dou u by dou x, dou u by dou y and dou w by dou z equal to 0. So, this is the basic equation which is called as the continuity equation, which is widely used for describing the flow in a medium. Now, force consider acting on fluids in motion. The different forces influencing the fluid motion are due to gravity, pressure, viscosity, turbulence, surface tension and compressibility, and these are all listed below. Fg is the gravity force due to weight of the fluid, it is a product of mass and gravitational constant. Then pressure force due to pressure gradient, viscous force due to the existence of viscosity, then turbulent force due to turbulence, surface tension force due to surface tension, and due to the elasticity property of the fluid you can have the compressibility force. Now, if a certain mass of fluid in motion is influenced by all the above forces, then all the above mentioned force components, then the Newton's second law of motion, according to which we can write mass into acceleration, will be the summation of all these force components. Further, you have its respective components in the x, y, z direction, as we have seen here. It is all the first one, I mean x direction, then z direction, then you have the y direction. So, all other things ax, ay and az are the fluid accelerations in the x, y, z directions. Now, in most fluid problems we neglect the elasticity force or the force due to elasticity and the surface tension. So, hence the equation can reduce to as shown here: gravity, pressure, viscous and turbulent, and this force can be called as, is known as the Reynolds equation of motion. And for in the case of turbulent flows, in the case of laminar flows, turbulence, effect of turbulence are neglected. So, that would result into the summation of gravity, pressure and viscous force, and this is called as the Navier-Stokes equation, which is widely adopted. Then in the case of ideal fluid, then viscous force is neglected, and hence you have only the summation of gravity forces and the pressure forces, resulting in what is called as the Euler's equation of motion, which we will try to derive in the next class probably. Okay, with this I close for today.